people here so they know what we are talking about here. So, first of all, my name is Edouard. I'm working for the Fondation Jeune Scientifique in Luxembourg. And we are doing this program here in the framework of a program called Science Next. And Science Next was a program designed to inspire young Fuerscher to take on the new challenges for next contests. We give them ideas, like on projects they could work on, but we are also helping them, for example, with workshops to help them present their ideas, show up on stage, and do everything right to put the best assets on their side when they are going to participate. And recently we had the idea of launching these small conferences because it's a way for us to be able to react to the scientific news and what's happening in the world. And as you probably know, you wouldn't be here otherwise, there was something major coming up in the last few days, namely the first release of the pictures of the James Webb telescope. Which in my opinion is something really major, and I hope you can confirm that during the whole small presentation here. But enough talking for me. I'm going to give you the speech here, so I'm just going to ask Marianne if you could introduce yourself in a few words so people know who you are. We introduce you a bit within social network, but can you use your own words to describe your position and what you're doing?
Hello, my name is Marianne Bausch-Koenig. And I'm a PhD physicist, an experimental PhD physicist, but later I worked for 2 years as a postdoc at the UC Berkeley in California, doing some more theoretical analysis. And then I worked 30 years for industry and was quite busy and did not follow any more science news because I also had 3 kids, which eventually became independent. And about 10 years ago, I had more time again, and I suddenly realized the enormous progress that astrophysics had made between the time I was at university and now. And I started to get very deeply interested in this on the theoretical side, a little bit on the practical side, but mostly on the theoretical side. And now I'm retired and I'm using my free time to do work with the Jeune Scientifique, also with EZERO, and I'm a free collaborator of the Astrophysics group of the University of Liège.
That sounds like you're the right person for today. And you're, like you mentioned, you're doing work with the Jonk Fuerscher. Like, people should know that you are actually a member of the jury here, and then you're helping in many ways, like for our activities. So, yes. And I'm going to give the speech to Elisa because Elisa is really relevant here because she's the young generation and she's been participating to the contest with an actual astrophysics project. Can you tell us a bit more about it, Elisa, please?
Yes, so I made a project about how the elements were created in the stars, and yes, the stars are mainly the thing that fascinate me the most of the space.
Can you tell us why, actually?
It's because we are actually all stardust, so the stars are a little bit like our ancestors.
So wasn't that something you were working on for your project, right? Like you worked, if I remember well, on the stars, like how do they actually build elements and these kind of things, right?
Yes.
Okay. Was it challenging for you?
Yes, quite a bit.
Okay, but you managed quite well, right?
Yes.
Yeah. Tell us, like, what happened after the contest. What did you win for prizes?
I went to the Deutsches Zentrum für Luft- und Raumfahrt in Cologne.
Which sounds like a dream to me, actually.
Yes. So it was also quite nice.
Okay, you enjoyed it. Yeah.
Yes.
Okay, and do you see yourself working in the future, like in the fields of astrophysics?
Yes, I think so.
Do you think it's going to be challenging, or do you think it's accessible, actually?
I don't know.
You'll see. You're a bit too young maybe for that. But first, congratulations for your participation and for winning this prize. And there is also something I would like to add is like you're taking pictures of the sky yourself, right?
Yes.
We'll probably show at the end some of the results, but like, did you receive some help to make those pictures, or like, did you start on your own?
Actually, in school, we have a teacher who teaches us about astrophotography.
Sounds good.
And so we learn there. I learned the basic things, but the pictures I took on my own.
Okay, then congratulations. I'll show them probably later. I'm also passionate about space and about taking pictures of the sky. If we have time, I'll try to show you some examples later. But we also have something in common here. So like you probably know why I'm particularly excited about what's happening with James Webb, because when I've seen the pictures appearing on my screen 2 days ago, I was like, oh my God, I was. I'm just going to ask you, how did you react to those pictures, actually? I'm going to start with Marianne. What was your first thought, actually?
Of the James Webb pictures, you mean
Yes.
now? Yes. Oh, they are absolutely amazing. If the precision is absolutely crazy, and also if you think on the complication to get this done on all the, I think there were about 300 things which could have gone wrong in the whole way from launching James Webb till its place where it is now, and the unfolding and the calibration of the instruments and so on. And they all went fine. So it's on one hand an amazing engineering feat, and on the other hand, I think it shows very much promise for science in future.
Yes, indeed. While you were talking, I actually started to show like the 4 pictures. Like, let's talk about 4 pictures, and there is one graph which is actually an analysis of spectrum, so it's a bit less photogenic. But I was talked about the level of details, of course. We are going to talk a bit about James Webb. I think you're well placed now. So it's a project that started long ago. Some people see that as the son of the Hubble telescope, like what's coming after is slightly different because it has other purposes as well. But can you tell us a bit more about the genesis of the whole project?
It started in 1996. At that moment, yes, as a next generation Hubble telescope. What could we do to go further? It's a collaboration of NASA, ESA, and the Canadian Space Agency. The latter two sometimes get lost, but actually it's 3 different agencies which worked on it, not only NASA, although NASA has a main job here.
Mm-hmm.
And yeah, the idea was if we want to go further, and there's several problems with Hubble. Hubble is in the orbit of the Earth, which is practical. So this is some problem you can go up with the space shuttle and fix it, yeah. But it is not in an ideal place to do infrared light. I mean, Hubble is a purely visual, while it has a little bit of infrared capability, but it's mainly a visual object telescope, because infrared spectra can only be taken by very cold instrumentation, and Hubble is not far enough from the Earth to be cold. Yeah? So you need one very far enough. And why do you want infrared? There's 2 reasons. One is because there's a lot of dust in the universe, and with infrared you can see to a large part through the dust. So there's suddenly things that become visible, which a visual instrument could never find. And the other reason is as the universe expands, wavelengths get shifted. Some call it the Doppler effect. Some speak of cosmological redshift. It's actually the same thing, but it means that wavelengths get slowly, with the expansion of the universe, the wavelengths get longer. So the further we look far away, which means back into the past, yeah, the longer wavelengths we will see.
I'm
And
going to try to use a picture that people always use, like to for people to understand that what we call Doppler effect is like basically when you hear an ambulance like driving the road next to you, first you're going to hear it with high-pitched tones, and then slowly it's going to no, 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 no. Sorry for my imitation, it was terrible. But you got the idea. And basically what James Webb can do here is record those low, low, low tones that the ear couldn't hear anymore, technically, so it's kind of an image. And Hubble would be able to be like similar to our ear, so it would see the same thing as us, sort of. And James Webb can like see much, much further in that spectrum. So it's like, it's not a perfect image, but like it helps to understand sometimes.
Yes, the big advantage is that the further we go back in the past or far away, the more information is in infrared and not anymore in the visible. Yeah.
Okay.
With the visible, we are limited.
I'm just going, Elisa, you probably know Hubble, right? You probably have seen the pictures of Hubble. When did you start to get aware about the existence of James Webb? Do you remember that?
I think about 5 years ago. I'm
Okay.
not sure. Yes.
Okay, because to me it was kind of strange because like we didn't hear so much about James Webb. I guess it's because Hubble was efficient enough for a while, like it was more a closed circle. But did you understand quickly that it would be something major for science and for astrophysics?
Yes. When I heard about it, I was already really excited. So
Oh, okay.
since then, I did some research about it and tried to catch up news. So yes.
I'm going to ask you both a question, but I think it was on Christmas Day, if I'm right. Were you in front of your TV to watch the launch?
I was, yes.
I was
Yes,
too.
Not the TV, the computer, but
Yes. So okay, so I was comparing that to some like the American people like watching football during the Thanksgiving dinner, and so many of us actually were watching the launch of James Webb, just like crossing fingers that it would not explode on the way, you know. So, like I think we've been relieved, and we received a nice Christmas present that day, I guess.
so just to go
Please.
into a little bit more detail, so James Webb is actually positioned 1.5 million kilometers behind the Earth, opposite direction from the Sun. So the Sun, the Earth, and James Webb are aligned, and there's a point where there is less gravitational force because the forces at that point are
Yeah, it's called the
very low.
It's called the
The sum of all the it's the Lagrange L2 point where the centrifugal force is just equal to the attraction of the Earth plus the attraction of the Sun. So the total force on the object is small.
It's a stable point, right?
It's not a stable point. It's only a half stable point, a
Okay.
saddle point. It's a minimum in one direction and a maximum in another direction.
Okay.
But still, it's a stable enough point to minimize use of fuel, because that's a big issue. If you all the time have to correct the position of your telescope and it's 1.5 million kilometers away, then you need to have a big tank full of fuel for it to live long. So it gets placed at the point, it turns with the Earth around the Sun, and you need very little fuel to correct its position. It's not exactly at the L2 point because a lot of stuff is there, also some debris and so on, because in one direction is the minimum. So it's turning, making circle around L2, and that has the additional advantage. It can't be all the time in the shadow of the Earth because it has solar panels. It has fuel and solar panels, and the solar panels obviously need to see the Sun. Yeah.
Yes.
And that again means it needs insulation so that it can still be very cold. I mean, the Sun, of course, has not much power at that distance, but still it has protective layers. And then the solar panels, they reach the Sun. And then the instruments, they are at like minus 260, minus 270 degrees Celsius. Yeah.
It's next to zero, basically. It's not
It's next to very, very cold. Yeah.
Yes. Okay. I'm going to, for me, the most impressive thing, and you kind of mentioned it, is it's so far away from Earth that there is actually no possibility to go there and to correct anything if anything goes wrong. I remember there's like this. There's actually a movie where Leonardo DiCaprio is making the voice of. So it's like kind of a reportage, and he talks about Hubble and like what Hubble brought to the world, like in terms of pictures, in terms of inspiration. And there is this story that at some point they had to correct something because there was something wrong. And also like astronaut going there and then doing manipulation on Hubble itself, like going out in the space and then like having to punch things so it goes inside. So it's kind of rocket science here almost, you know. And here with James Webb we have no margin of error at all. So that's what impresses me the most. Elisa, what during the whole thing, like we mentioned, for example, this system for making the thing stable, this system that keeps it really low temperature. There is the fact that it's so far away. What impresses you the most, actually, in terms of fabrication, launch, and what talks you the most in the story?
Actually, that everything has to be 100% correct and that there was no place for mistakes. So that is almost perfect. Like
There is a saying which is we always say that there is the 100% correct doesn't exist. It's not possible. So like we still had to plan for a margin of mistake. But like, were you scared at some point during the launch, or like were you confident, or how was you feeling about that?
Actually, I was quite confident, but yes, I was always hoping that everything goes right, and yes.
Okay, because we have to remind people that it took it took decades to design, to prepare, and it costs like probably twice as much as it was originally planned, which is something like $10 billion, if I'm right.
Yes, it's $10 billion, but obviously it also took from 1996 to now, so it
Yes.
took a lot longer, and the money was spread over all this period. So you have to take that into account, that it was a very long project.
And like in terms of security, people have to imagine that like any part of the telescope could go wrong because there is a lot of mechanics as well involved. And so we have to make sure that if there is a problem and this problem goes along and then goes further, like it can really mess up the thing entirely really quickly. So we had to make absolutely sure that everything was right and working properly. So this is an absolute performance. And there are so many people who worked on it. It's just a marvel of cooperation. It's maybe something we could point out because there were so many scientists around the world like working all together on that project and making it work all together. So what's your feeling about that, Marianne?
It's a wonderful piece of cooperation, and it's well done. The mechanics had to work. The electronics is to a large part double. So if the first electronic circuit wouldn't work anymore, there would be a backup circuit. So they did build in some resilience. Yeah.
Mm-hmm. Another
The
thing
biggest issue for the moment is that even in the vicinity of L2, there's a lot of micrometeorites, so little pieces of something floating around here. Not debris like there's in the Earth orbit, but really pieces of some meteorites or stars, and dust more like stars. But and one has already hit and done a
that was my
little
next
dent
point.
in the main mirror. So and it's maybe 3 months at its position. Yeah. If it's a luck thing, then it's not bad, yeah. But if it suddenly starts to happen continuously, that I mean, it's supposed to work for about 20 years.
Mm-hmm. That's a story of balance. You mentioned fuel earlier, so it means that the James Webb Telescope was originally planned for a certain duration, and if I remember well, during the launch, and that's maybe a good thing for Europe, but the Ariane 5 launch was so good and so well prepared that it actually saved some energy for James Webb to actually reach its target and they managed to augment the actual potential lifetime of James Webb Telescope, right?
Yes, but the augmented lifetime is now expected to be about 20 years.
Mm-hmm. Which is enormous, I think, like compared to what's there.
Well, Hubble is longer already in use, but
Yes,
in
indeed.
Hubble you can, if need be, you could change batteries.
What's going to happen to Hubble now, actually?
Well, it's normally supposed eventually. The initial plan was to send a shuttle up again and take it down
Okay.
entirely. But obviously, there's no space shuttle anymore. That's the
Mm-hmm.
disadvantage of something being working for 30 years. The world changes in the meantime.
Mm-hmm.
And so the actual plan is to eventually let it fall into the Pacific Ocean.
Which is a terrible story. I can't imagine we let them down. We let it down like it's been a good
Well, if it
friend, but
doesn't work anymore, I mean, Hubble is already on a number of instruments on this B electronic circuit. Yeah,
true.
it could seriously have any issue one of these days, and if it suddenly can't do work anymore, then
Mm-hmm.
there's no point in having it in the orbit, and then it will fall down any place eventually without control. Then it's a much better thing
Yeah.
while it still has fuel to make it go to a place where it doesn't bother anybody coming down.
Mm-hmm. Now that we compare James Webb and Hubble telescope, I'm going to place one of the pictures, like probably the first one. You have it in mind, ladies. The first one I would like to show to people is what's called the deep field. So it's been the first picture that was originally released.
Yes.
I think there was a ceremony at the White House where it was first shown to Joe Biden as a proof of good cooperation, let's say. And it was like one day before the official release. Can you describe, maybe Elisa, what we see on the deep field picture?
So on that picture, we can see a lot of galaxies that have different distances to us, and yes, it is really detailed, and its resolution is also really good, and the exposure to take this picture was actually not really long compared to the deep field of Hubble.
Yes. So, if I'm right, and if I would have to compare, it's like the feeling I had when I saw this picture, and maybe you can confirm or infirm. But to me, it was like, okay, we. It was one of the major photos of Hubble, actually, deep field, because at the time they had this idea of pointing the telescope in a zone where there was nothing much happening to see what we could actually uncover, and they were really surprised of like seeing how much there was. And it's probably like nowadays it's maybe not the most impressive visually photo from Hubble, but it's probably one that left the biggest mark on people. And now, like this James Webb telescope is only operational since like a few days, let's say. Let's count in days, and then it's here to me. This photo is here to show the muscles. You know, it's like coming out of the gym and saying, like, see what we can do already better in just a few days than Hubble did, like in years. Like, did you share the same feeling?
It's mind blowing because the oldest object that Hubble Deep Field saw was 800 million after the Big Bang,
Mm,
so about 13 billion light years years ago. And now, and that took weeks and weeks of Hubble. And now they did this picture in 12 hours,
crazy.
and it shows objects which are older than that. Yeah. And among them, one galaxy which is 13.1 billion years old, so 700 million years after the Big Bang, and we have a spectrum of it. We see hydrogen, oxygen, neon, so we know that's clearly not a first generation star. First generation star only consists of hydrogen and helium, uh, and I find that absolutely impressive that the very first image done in a very brief amount of time already is massively better than anything Hubble ever did. Because of course, having the spectra, being able to say what elements are in the star, will answer all these questions that are now on in the science, in the astrophysics community, on how the first stars formed and how the first galaxy formed, and also the importance of dark matter on that, and all these things. And some people think, good, you have different people saying different things, but I think Webb will certainly be able to go like 500 or 300 millions after Big Bang. Some optimists say 100 million. I saw one website which claimed it could go 50 million. not sure that is true, but still, once it starts seriously working, it will get another huge leap further than this nice image that we saw now. Yeah.
We just need to understand, so for the people first, like the light needs a certain time to travel through space. So like a telescope like James Webb or Hubble is not so like it is a visual instrument. It allows to see things like bigger, but that's not exactly the most like the most potent use, I would say. It's like we are trying to see things like back in time here, so it's like a time machine. And there is a point where after what we call the Big Bang, where light started to spread, and there is a limit to that. So basically we are almost reaching that limit here with James Webb. So almost like
Yes.
I mean, like if we are talking about 50 million years or 500 million years compared to the 30 billion years that's the lifespan, like it's a very young universe that we see. That's what I'm trying to say. It's a very,
Yes.
very young universe.
We should reach a point where we see how the first galaxies formed. And obviously the dynamics was quite different from now because the universe has massively expanded since then. But at an earlier stage, this was all much closer together. So there's much more interesting dynamics, and that's clearly something that a lot of people are waiting for.
What kind of questions can we answer with that, actually?
We can first, if we would see the first generation of stars, which consist, according to the standard model of cosmology here, the so-called lambda CDM model, should consist only of hydrogen and helium.
Okay.
Now, obviously, that would be interesting already in itself to check. Are they made up of hydrogen and helium? And according to this model, the Big Bang produced hydrogen roughly 75% and helium 25%, and a tiny little bit of lithium, but let's say mainly hydrogen and helium. So we could check on that. And then how is the buildup? I mean, is there first a huge amount of stars of mass, of gas, which then breaks down first in galaxies and then in stars? People now think that's not the way. They really think that there's local places where stars are formed, and the stars are then slowly attracted together in galaxies. And then there's something called dark matter, which is something we don't know much about. It's a matter that only interacts gravitationally, which means it's not influenced at all by light or any electromagnetic spectrum wave here. And this dark matter, therefore, we can't observe with our telescopes because they're basically wavelengths, electromagnetic based. Even if it's other wavelengths, it's still electromagnetic spectrum. And we think that as dark matter cannot lose energy so easily as normal matter, which can radiate energy away, dark matter has first clumped, and then where there's a lot of dark matter, the galaxies formed.
Okay, clusters.
Yeah, later clusters.
Okay.
It's bottom up, yeah, stars and then galaxies and then clusters of galaxies or maybe superclusters. But with the influence of dark matter very strongly. What we can know about why we know there is something called dark matter is because obviously as it interacts gravitationally, we see it in the way the galaxies move here. If you look at the speed of the stars at the outer rim of the galaxies, it's too high for a normal. If there was only the visible matter, so they know there's something more.
So if I reformulate, it's like we are able to see with our telescopes and some high performance telescopes like Hubble or James Webb telescope or other instruments, that there are some, let's call that anomalies, if we compare that to our models. And those anomalies could be explained by dark matter or dark energy, but we have no much clue about what it is about or what's the composition of that thing, and we are trying to understand what it is, and that's one of the ways, right?
Yeah, dark matter is the gravitationally interacting bit, and that tells us how the mass is clumping and forming, whereas dark energy is the thing that makes the universe expand. And obviously, if we can go much further backwards in time or farther away, it means we can measure the speed of expansion of the universe much more precisely. And that's another very big open question in science, namely how fast does the universe expand? It's the Hubble constant,
Indeed, yeah.
where there's several methods to measure it, and half of the methods give a value around 74 and the other half a value around 68. So James Webb could give us some new inputs and settle finally this question.
So I'm going to invite Elisa to work on that project here and try to find what dark matter and what dark energy are, just based on the James
One
Webb
of them would be good already.
No, it's she's an alumni Jonk Fuerscher. She can discover both, I'm sure. But is that something fascinating to you as well, Elisa? Like this dark energy and dark matter issue?
Dark matter more than dark energy, but I never went really into detail with that.
Okay, it's probably because we don't have so much details about it so far.
Yes.
Just to point out, I read some figures, but like some people say, so baryonic matter is like the matter that composes our universe. Like it's like basically everything that we know. And if we just check the model, including dark matter and dark energy, baryonic matter would account for maybe 5 to 10% of what's out there in the universe. So it means that 90% we have no clue about, basically.
Yeah, more 95 actually.
Something like 95. So there is still a lot of work, even though we believe we have a good understanding of our universe, the matter, how is the matter made, what it's composed of, like most of the interactions. And we've seen that with the Higgs boson not so long ago, like that the models are more and more precise. But we shouldn't forget that actually, like if like this theory is right, then it's only 5% of what's out there. So yeah, that's kind of scary to me, actually.
Yeah. The problem, of course, is you can't do experiments in a lab anymore. You have to look at what happens to be out there and then deduce things from there, which makes it more difficult to advance. And let's say, if you want to understand about electricity, you could build 200 years ago. They would start building circuits and experiment around. Yeah.
I'm just going to show now the planetary nebula and Stephan's quintet pictures. So first I'm showing the planetary nebula here. So where we can see on the left side, there is the actual like visual picture. Let's call it that way for simple reasons here. And on the right side, there is a more infrared version. And I'm just going to move as well to show the second one that we've seen that was also really impressive, which is Stephan's quintets, where you can see a few like galaxies interacting with each other on a really small patch of space. What was your impression when you've seen both those pictures here? Elisa?
I was really impressed by the Stephan's quintet.
Okay.
Because I really like pictures in general of galaxy collisions. And I also really like that the picture of the ring nebula was taken in near-infrared and mid-infrared.
To be able to compare.
Yes, exactly.
How about the level of details? Like, did that impress you? I think that was what's most impressing to me, actually.
Yes, to me too, because I also really like that in one picture of the ring nebula there was that galaxy on the side, that long galaxy.
Yes, indeed, yeah. Like
also the core of and also the core of the nebula.
If I remember the press conference, like one of the guys working on the project thought it was first part of the planetary nebula, and then they had some sort of bet when another said no, it's actually a galaxy seen from the side, and the guy lost because it was actually a galaxy that you could see through. But it shows like the insane amount of details that we see within the nebula, but also what's behind and what the telescope can actually spot, and with such a great amount of details, which was insane to me.
Yes, to me too.
Marianne, what was your thought on that?
Well, it's first a pretty picture, and there I want to say one thing is infrared, we cannot see infrared light. I mean, that's why we have infrared cameras for heat or to see where a house is losing heat, that sort of thing. So we have to remember that these pictures are in false colors, because the actual wavelengths are infrared wavelengths, and so they translate them according to a certain pattern into light that we can see with our eyes. Yeah, because that of course makes it easier to understand what we see.
I'm just going for the sake of because the thing is, like, people tend to think it's completely inaccessible, and you just need a $10 billion telescope to see these kind of things. I'm going just to place like two, if I see them here, two pictures that I made. I don't know if you would be able to see that, ladies, on your screen, but the viewers would be. It's like galaxies and nebula that I've taken like with a really cheap telescope from my balcony. So like I spent a lot of time doing that. But there is a first one here, which is also in terms of details quite impressive. Like if you consider that it was taken like again with a cheap telescope from a garden in city, and another one which was a nebula. It's called the Rosette Nebula. It's something that you see in winter, which is also really impressive in terms of like colors and. But those are huge objects in the sky, and even though we can photograph that from our garden, like this instrument can, James Webb can take pictures of much more details, and details that we wouldn't be able to access otherwise, and like helping us to understand the mechanics within those objects, right?
Yes, obviously the pictures show, for instance, the planetary nebula, the Southern Ring Nebula is a dying star, and we can understand, therefore, the details on how a star dies and throws out dust and matter and gas.
Yes.
On the Stephan's quintet, we see all these rings. We see on the topmost, not rings, sorry, galaxies. And the topmost galaxy, it is a galaxy with an active galactic nucleus, which is a black hole, actually.
Yes.
It is a black hole which has probably 24 billion sun masses here.
Which
And they are
is so
now
hard to
taking
grasp.
spectra of these. So they take spectra of, not of the black hole, because out of the black hole nothing comes out, but all the matter that falls in the black hole gives off a lot of energy while it falls in. And this light is now being analyzed with spectroscopy. That means we can say which elements are this. Is this dust, so silica, or is it gas, hydrogen, or
So what I'd like for our viewer to grasp here is that basically those are pretty pictures. They are really impressive and they show majestic objects in splendid colors and details. But they are also really important to understand like what's the mechanics behind it. So like with so many details, we can actually try to explain the mechanics behind, and that's also a major part of what James Webb is about.
Yeah, we probably wouldn't have spent $10 billion
No.
on
On an
doing nice
artistic
pictures.
project, yeah. Sadly, the art just that's one question. Maybe you can answer that. I couldn't find the answer, but for Hubble had in its planning some slots for people to be able to produce majestic pictures. It was just like some sort of artistic slot. I mean, like artistic is a big word here, but it was meant to make pictures that we would believe would be nice and inspire people. So not so much on the research side, but more on the visual and inspiring side. Do you know if there is anything similar planned for James Webb?
Well, you see it in a sense. If you go on the NASA website, it's a lot about the color and the beauty of the images. And if you go on the ESA website, there's a lot more details on the science. I actually prefer the ESA website, which has more detail. But very clearly, the NASA people choose very well the 5 images that they started to show on July 12th. Yeah, and some of them had to be pretty. That is also obvious.
Yeah, I'm going to move quickly. Like there is one that we can't really show, but it's like a spectrum, as you say. Like James Webb is able to analyze spectrums, which would be also very interesting to explore exoplanets in terms of what they have in their atmosphere, and if we can find traces of water or like elements that could be bricks for life and this kind of thing. So that plays an important role. I'm summarizing here. It's much more complex than that, but that's the idea. And there was another last picture which was shown, which was also majestic. This is like for me really what I'm talking about when I'm talking about the visual aspects, the impressive visual aspect, and like the colors and the shapes, and it's almost art. It's like this Carina Nebula that they showed here. They showed it last. I think there was a reason for that. It's because they believed it was the most visually impressive, wasn't it?
I think, yes. Well, obviously, they choose a dying star and they choose a star-forming region. So there's a scientific logic behind that as well in the 5 pictures here. But the star-forming regions, everybody knows that star-forming regions give spectacular pictures.
I'm going to show it again here. And for people to understand what they see here, those are gigantic, but I mean really gigantic clouds of dusts. And some parts of where it's particularly dark is called dark nebulas. And it's where this gas and dust cloud is collapsing onto itself and form new stars. So it's basically the place where stars are born.
Yes, it's...
And to come back to Elisa's projects, where stars are born, like they produce new elements that could potentially lead to life like us. So it's really important to actually understand our origins in a way. So it seems far-fetched, but actually it's kind of the goal here.
Yes, maybe we talk briefly about exoplanets, which are planets which go around another star, not the sun. Yeah. And the crazy thing is that when James Webb was initially planned, exoplanets were absolutely a minor research field. The first one was detected in '95, but people didn't really believe it initially, and there was very few people working on it. And sometimes by serendipity, James Webb in the end is now a wonderful instrument to study these. Because obviously what we want to see if we find an Earth-like planet, which means a solid planet, not a gas-like like Jupiter or like the WASP 96b that they show, yeah, and find a spectrum with water. On the WASP 96b, it means nothing that there is water because it's a huge planet, much bigger than Jupiter, and it's very close to a very low energy star, yeah. And no, sorry, that's the one that goes around the sun-like star, but very close. It's much, much closer than Mercury to our sun, and it makes one orbit in 3.5 days.
Which is
so
very, very fast.
It's hotter than 500 degrees Celsius, yeah. So at least life as we know it could not be there. It's just to show the principle. But if one day we get the spectrum of, for instance, the next system they want to analyze is a TRAPPIST system, where a low energy star with 7 planets has some in the habitable zone, which means the zone where life could theoretically be possible. And if there we get the spectrum with water, that would be interesting. It still doesn't prove something, but it's certainly interesting.
So it's literally the quest for another form of life indirectly.
Yeah, we probably would never be able to communicate with these people because the light transmission is way too slow to do that. Yeah. But still, it's interesting to know if our Earth is the exception. There's been more than 5,000 exoplanets detected now, but there's only 30 or 40 inhabitable zones and hard solid-like. But that's in part due to the way we detect them. So we are very good at detecting very big Jupiter-like planets near very energy-poor stars. Yeah.
Okay, but
so that's most of the 5,000 fall in that category.
I'm going to do a small recommendation, but there is like this trilogy of books. Sadly, I don't have the author names in mind, but it's called the Three-Body Problem Trilogy. And if you read this trilogy, which is majestic and fantastic, it's one of the reasons that got me into photography, they explain you pretty well that maybe it's not a good idea to try to contact other civilizations in space. I leave you for the discovery, and but the free body problem, I recommend the reading. I'm just wanted to come back to Elisa now, because one thing that they stressed, like during this whole presentation, was so the duration, like they estimate. So, one of the persons said there is science there for the next 40 years. Like we talked about it a bit before, maybe it's a bit optimistic, 40 years, but nonetheless, like 20 years wouldn't be silly. And so that means that people like you, Elisa, or people that are not yet completely born, would be maybe working on James Webb data. And we call this discussion, what does the future of physics hold for our young scientists? What are your hopes? Like what do you hope the most, like with James Webb? Like you said earlier that you had a big interest, like when you heard about it and about its complexity, and that it's the first image are crazy. And but what can you imagine what would be in the future for people like you in astrophysics and with this type of instruments? It's a
Well,
difficult question, no?
yes. So it depends also what the astrophysicists now discover in the next year. So what will be left for us?
Yes.
But I really hope that the formation of the first galaxies, and so these things will be discovered. Yes, also about the formation of the elements in the first stars. So yes.
So there is a bit of everything for you there, if I understand well. But you
Yeah.
have a bigger interest in mechanics, in celestial mechanics, if I understand that well as well, or?
Yes, in fact, yeah.
Okay, so that's one of the reasons why Stefan's quintet was particularly appealing for you.
Yes.
Okay, I understand that now. And what do you think we can expect in the future? Like where, if you had to do pronostics, where do you see there would be the first surprises? I'm asking you both here from James Webb. Like a surprise is a surprise by nature, yes, but what do you expect the most? Like what would be the biggest surprise for you if they announce something crazy in the next 10 years?
Well, the big surprise, or maybe the big hope that some scientists
Yes,
have, is that you
hopes is
find
the right
something
word.
which invalidates the standard model of cosmology, which shows
That's an
that it
excellent
still
point.
has some a few issues there. So some things which we understand very well and others less.
I'm just going to interrupt you here because it can be a bit puzzling if someone says that what we expect the most from James Webb telescope is that the telescope would tell us that everything we know is wrong. Can you develop a bit on that thought?
No, I don't think it will show us that everything we know is wrong, but it might show us that there is a few points in the model where the model is oversimplified, where it needs more elaboration, a deeper level, an additional level, for instance, anything involving dark matter or that sort of thing, and also some other interactions. And I think that's basically scientists want to improve their theories, to push them further. Yeah.
Yeah,
And so that's what would be certainly interesting.
it's where we
It would
see the,
also be great if it confirms everything. I
yeah.
mean, then we say, wow, we have a good model. And but obviously, if we can push our model further, then we learn something new.
There was like, if we come back a bit in history, there was what we call the ultraviolet catastrophe. You probably know what I'm referring to,
Yeah.
but there was this like model in physics, including some modelization for curves for ultraviolets, and people noticed that there was something deeply wrong with the model when
Black body radiation.
the black body radiation, and then they realized by experience that the model was actually not right in some ways, but they couldn't figure out, and that's basically how we developed the first theory of quantum mechanics, because we had to find a solution to reconcile like what we've seen with experiments and what our theoretical progresses were showing, and like this combination of two like led to the discovery of quantum mechanics, basically. So if we have an instrument that show us that there are some parts of our model that are wrong, it's a mean of maybe developing a new branch of physics or something that we don't know yet. And usually it's like opening a door to something new, basically.
Yeah, just for the story, young Heisenberg in around 1900 or 1905 was thinking about studying physics. And one old physics professor told him, look, physics is all done. There's a small problem left with the ultraviolet, but that's a minor thing. Don't worry about that. Yeah. I would say you should study biology. There's much more to go in biology here.
Oh, Lord. Oh.
Heisenberg decided to go for the physics, and the whole of quantum mechanics came out. Yeah.
Yes.
And from Einstein later, good, that has nothing as another point, but the general relativity, I mean, viewed from today, obviously physics was not at all done in the year 1900. Yeah.
Yeah, so see, Elisa, you have plenty of room for an excellent career full of discoveries. Don't give up now. It's too soon. And I just wanted to point out, so we are talking about like really expensive instruments and like high-level astrophysics. I'm coming back to our Jonk Fuerscher contests team here, because Elisa, you made a first project which was about molecules formation and atoms, like the fusion process and what kind of atoms could be created within stars, and you explored that. It was a biographical work, wasn't it? So you didn't do any experiment or data analysis.
Yes, exactly.
Okay, a biography work. I just want to point out that those things are actually not as accessible as they seem to be. Elisa is one of the proof that you can actually start a biographical project by analyzing books and trying to gather some theories together to present a project. There is another thing which is really, really interesting. I mentioned earlier to you, Marianne, that all James Webb Telescope data is actually open for public, which means that you can download them. And if I know some people, like you can on Flickr or Picasa, those photo platforms, you can easily find some people who actually gathered some data from Hubble telescope and tried to process them their way, so they would get their own nebula photo, and based on their own processing scheme. So you can do that in James Webb Telescope too, and it's actually not that hard. I would suggest young people, for example, to check on softwares like Nina or Serial that allow you to process photographs made by telescopes and then build them together so you get an actual image, which is very interesting. I asked you a bit before we started this presentation if you could come up with some ideas of what Jonk Fuerscher could start as a project related to astrophysics. Did you have any suggestions maybe, or something that you could see that would be easily done by Jonk Fuerscher?
I don't know if it is easily, but I also I knew that it is important to do also practical work. So I also thought about the spectral classification of stars or
Okay.
something like that, or determine the distance of objects, but I never really had ideas how to calculate that. So I don't think that it's really easy. So yes.
I'm going to make you a small suggestion based on experience. I've seen during the contest, for example, I think it was last year or the year before, three young Fuerscher presented projects based on earthquake analysis and like the waves. And so they started and they had this idea and they came up with a project which was really interesting. And in the jury, one of the jury actually provided them later with actual data that he had access to related to earthquakes and like those waves, and he helped them actually to process those data and gave them some clues about what you can do to handle such big amount of data. And I think, if I'm not wrong, that they are working on it at the moment. So if you have an idea like that and you need access to data or methods or I don't know, anything, you can basically just ask us, and we are more than happy to help and to put you in contact with the right people. Because most often, the most difficulties in this type of project is to start, and the biggest challenge is yourself. So it's like you don't believe that you can do that, but with the right help and the right people behind you, actually, it could lead to something great, I think. So keep that in mind, Elisa, because and if people are listening to us and they want to do something like you suggested, they're more than welcome, and we'll help them. Marianne, did you have any ideas for that?
Well, I thought about doing some practical work with near-infrared or infrared spectrometers. Obviously, you have to find someone who owns one, but that's probably, as you say, if we look around, you probably can find, and then compare with the spectra from exoplanets. Let's say something that you model in a lab. That might be interesting.
Yes,
Gives you a more practical interest and understanding of what they are actually doing. Yeah.
There is also something, I'm just going to show you something here. This is my telescope here, so it's not as big. It's like a tube with some mirror, so it's something like that can stand on your balcony here. And more I've seen popping on the internet and everywhere some science participation projects. And it's something quite big in astronomy in general, because it's one of the rare fields where amateurs can actually still discover something today. So they really are on the look, like, I mean, scientists, they are really on the look for data gathered by amateur worldwide, whether it is about like planetary nebula or comets. Comets are an important thing. Meteorites as well, to help people to locate where they actually fall on Earth. And all those data can be gathered by amateur astronomers. And so I highly suggest you, if you have a slight interest in looking at the sky, or if you have access to a small telescope, just to check online, because there are plenty of projects that actually need your help, and where you don't need to have a PhD. You just need to be an amateur with a bit of passion, and that should be enough, actually. So like, it's not, you don't need a huge budget. All you need is like goodwill and time. Another project that I had in mind, maybe, which is a bit far-stretched, but you know what SETI is?
Yes.
Elisa, do you know SETI?
No.
So SETI is the acronym for Search for Extraterrestrial Intelligence. And it's basically, which telescope is gathering the data, Marianne? Would you know that?
They, well, a lot of work is done with the array of radio telescopes in
Yes.
Arizona. Yeah.
It's
Some of which broke down recently. I'm not
Yeah.
sure if they're up again.
It's mostly radio in any case. And so it's a project that asks computers all around the world, when they are not working, so you know your screensaver, they actually ask your computer to process some data while your computer is not doing anything else, like in hope to find some patterns, and to maybe at some point, with a bit of luck, maybe with a lot of luck actually, but nonetheless to try to find extraterrestrial intelligence. So that could be also something.
It's a long shot, huh?
It's a long shot, but with luck, who knows?
Yes.
Okay, did you have anything that you wanted to say to our Jonk Fuerscher as a closing words? Like, I'm going to start with you, Marianne, something for the future that they can hold, or for the contest, or...
Science is never complete. There's always new questions. When you learn something, you at the same time usually find 3 more new questions, yeah, if you solve one.
That
and
sounds
therefore,
awesome to me.
Don't think, now I'm born too late, I can do nothing. That's wrong, yeah.
That sounds very, very good. Yes,
yeah.
And Elisa, if you had to say something to some people interested in the Jonk Fuerscher contest, but they didn't do the steps yet, with some words of encouragement, what would you say to them, actually?
Yes, also that there are still new things to be discovered, and I don't know whose quote it was, but the things that we know are a drop, and the rest that we don't know is an ocean. I don't know whose quote it is, but yes, I think the universe is also reflecting that. So the dark matter and the dark energy are 95%, and the rest 1%. I think that's...
So there is still a lot of work. Okay, so like, thank you for your time. Thank you for the inspirational talk. I hope that we'll get some people more intrigued about James Webb Telescope and that we were able to provide with some interesting explanations. I'm going to go through like the usual thing, which is like based on YouTube. But like, if you like this video, you need to click the thumb up, of course, or share with your friends. Don't hesitate to come to us or ask Marianne or Elisa if you have any question. Like, we will be here to answer you. And if you have some questions about the Jonk Fuerscher contest and you would like to participate within the field of astronomy, or whether it's psychology or whether it's biology or anything like that, just contact us because we're here to help. And as you can see with Elisa, it's completely worth it. She participated with a project. She won like a trip to the DLR, which is one of my dreams actually. So I guess I would have to participate as well. But you went there, so it's like I'm jealous now. But thanks a lot for your time and for your help, and hope to see you soon. And any last words?
No, not really.
So we can say bye as a last word.
Yeah. Bye.
Thanks a lot. Bye.
Bye.